No.
All right. Well, um, I'll start, I guess, the way I have in the past, with just a review of the agenda. Let's see, I have it here. Share. Um, so um, I I've agreed to. I should have changed that from saying tentative. So I agreed to be in terms of upcoming presentations that I would try to make a presentation next week on the subject of geometry in particular. The main reason for wanting to do that is that it was motivated by what Gerrit Sobczak was saying in his presentation on geometric algebra, which begins with the presumption that we all understand what is geometry. But it occurred to me that especially from the point of view that was promoted by Dr. Shevich, this is far from clear and perhaps even controversial. So, but it's fundamental to some of the approaches, and I think it's strongly related to the interaction theory that Dr. Cruz is going to be discussing today. Um, so I think it's good to review that. I know Dahlia, you did quite a bit of presentation on this, almost essentially the same subject earlier in in the year. So I may be repeating some of the things that you said. Most of the resources that I would call on probably come from Zbigniew-Shevich's unpublished class notes and so forth, just as you were discussing earlier, Dahlia. So, but some of the people who are here now may not be familiar, and I think it would be very good to review this whole idea about exactly what are vectors, what are covectors, and what is geometry in general. So that's what I'm hoping to talk about next week, but I'd like to make it more of a discussion, I hope, rather than a presentation. But, okay, and also I do encourage everyone to provide suggestions for continued presentations after that time. I know that a break is coming up for many people. So we might also decide just to suspend the seminars, but I think we need to discuss that next week, and hopefully perhaps other people would come forward. I know Dr. Santilli was especially interested in continuing his presentations, and there's an overlap again with Santilli's ideas about isotopy and its relationship to geometry, which I think is interesting to follow. So perhaps he'll be able to do that for us. And okay, so with that in, I would like to invite Jesus Cruz to give us a presentation. I understand that it will be a continuation of the subject of the theory of interaction, and I am especially interested in these sort of foundational issues when it's relationship to um, associativity, the assumption of associativity, which lately for me in other discussions, for example, with um, Dr. Kotsan, in relation to relativity, the notion of associativity becomes really critical, and many people seem to bypass it entirely especially when they're thinking about velocities. But I think in the interaction theory, this has to come up quite early, as an important concept. So with that, I'd like to say to Jesus to please continue, and I look forward to what you have to say.
Okay, thank you. Thank you very much. I am going to start with this. I'm going to share my screen.
Yes.
Okay. When I prepared this presentation, I was worried that the idea is to discuss again the concepts that I was presented before. Then here is only a short review of the principal concepts that I was using for this subject. And then we are going to start directly with the ideas in the category of interaction systems and the principal definitions. Then, okay. Here's the starting point. The class of this category are formed by bodies in equilibrium state. This is the name that I am using for the classes of objects in this category. Yes. Then it is important to say that every time we think that the natural state of the bodies is the equilibrium state, and when they are put out of equilibrium, they tend to go to equilibrium again. Then this is the principal idea. Yeah, and then we can speak here about inertia, like one similar definition of equilibrium state. Then this is, yes.
Yes, sorry, I don't mean to interrupt, but I was wondering whether you would like to take questions while you speak, or can we wait till later?
Anytime is okay. Anytime is okay.
So I do have one quick question related to equilibrium state, and that is I was going to ask about the relationship between conservation and equilibrium. That you might describe a body as having as conserving something, as a kind of something more general than equilibrium, perhaps.
Okay. I think that when the idea of inertia is put it here, is to say that it is a natural tendency of the bodies to state in equilibrium, and the interactions is put the system out of equilibrium, but a system by themselves not go out of equilibrium because there are not outside interactions that break this. This is the idea. I understand your idea that maybe we can say that there is some conservation law in this expression, but I don't know if the idea of conservation have to be with the description, the particular description of the system. For example, in here, there is one more idea in this picture, because we speak about the category of body in equilibrium state. But the equilibrium state is here corresponding. Excuse me, I want to make use of this. Okay, maybe not. Maybe this. Okay. Then the idea that, as I said before, is that the description of the state of a body, for example, in an equilibrium state, no, is using scalar sets of scalar fields. And then here in this picture, we have one example of this kind of the description that I said before. And then one system maybe is in this corresponding to this equilibrium state. The system have not have any modification of this equilibrium because the set of parameters that are describing this state are constants, and then here comes the idea of conservation. Then we can say that, for example, this I am using better the blue one, no? This scalar, this element of the scalar field are in equilibrium in around of this, but at the same time we need that the system looking to this other one scalar field have the same value. Then there are some kind, certainly some kind of conservation here. For example, in the black one, maybe in this boundary of the point, the system is in equilibrium in this way. Okay, then we have here maybe some conservation law, but my first idea was not in this way, no? But maybe if
Can I
we
ask, let me ask just for clarification that now this graphic, it illustrates 3 different scalar fields, is that correct? Or
yes, I'm
and-
going to put some notes here. This is
okay.
F.
And you didn't specify any particular meaning for the 2 scalars involved, right? Yeah, so F and G, yeah.
F, G, and H. No? He have here, for example,
Yes.
and the set.
So in thermodynamics, for example, you would consider
For
pressure,
example,
temperature.
for example, the thermodynamics. We have here pressure, density, and temperature, for example. No? And those are describing the state of the system. But maybe
the
we
manifold,
are, excuse me.
the manifold itself, you haven't associated any meaning with the coordinates.
The manifold. Okay, here I am not speaking of manifolds, but one scalar field that is referred like one ring, one ring. Then I am speaking only about these elements that are elements of the scalar field. Okay, I represent the scalar field in this way, and then if G and H are elements of this. But I'm not speaking now about the manifold, because if I want to speak about the manifold, I think that we need another level, another level for the description. For example, here is the states, physical states that are part of the manifold, and then here, okay, here in this level, I am putting the elements of the scalar field that are used for describing this, and only when I relate in this way, I look for values of these elements of the scalar field and take them to reals. But the idea is that we only have the description here.
Yes.
Only here.
Okay.
Then in the pictures, I have only one graphical description of the level curves of the of each element of the field. Only that. only that. And then I said that this set of elements that I have here are the description of the state of the system. This is the idea here. Okay, and then with this, we speak now about the other elements of the category theory that are the morphisms. Morphisms are used for look about the relation between different bodies or objects of the category of the category. Then the morphisms are describing the interaction process, and then the action of one body on another body are described here. Then, okay, we have two principal elements here that are objects and morphisms that are the principal elements of one metagraph. And with these two, I can build one kind of graph that are describing the interaction in the system. I wanted to put here, for example, that each one of these objects maybe have different kind of description of their own state. That is, the states are not equal, and they are not necessarily described with the same set of elements of the scalar field. For example, here I can have for description of the system maybe if H1 and maybe another more, for example, G1. And perhaps here I have only if 2 G2 and another description totally different from the first one. All of them are elements of the scalar field. All of them are elements of the scalar field, and each body have their own set of parameters that are describing the system. But if I, maybe later, but if I take this like a system, Then all of these parameters, the system is totally described by the union of these two sets. Then
I have a suggestion for an example, perhaps. An example that I'm always very interested in, and I've followed in several different ways, but it's fluid dynamics done with multiple fluids, so that you have multiple interacting fluids. This is interesting, for example, in plasmas, where you can treat the electrons as one fluid and the ions as another fluid, and they have separate densities. So in a sense, the one fluid is a different object than the other fluid, and they interact in some way. Is that a good model for what you're describing here?
Yes, I think that it is a very good model, but not only that, because I wanted to emphasize here the idea of subjectivity in the description of the state of each body. Each body.
Yes. Yes, I think I see what you mean. That in Euler fluid dynamics, one takes some kind of absolute frame and describes the fluid with respect to absolute frame. But in your case, you would like to eliminate this frame altogether and perhaps describe one fluid with respect to the other fluid only. Right?
Only that. Yes.
Yes, I see.
This is the principal idea here. But in any case, all the descriptions are based in elements of the scalar field.
Okay.
Because all of these are elements of the same scalar field.
Mm-hmm.
Yes. Okay. This is a second idea that I wanted to put it here, and the third has to be with the definition of automorphism. Then here in this we have the one of the axioms of one category that are the existence of automorphisms, but not only that, but the existence of one identity. But first, it is important to say that we are speaking about here of automorphisms that are relations between inside one one object, inside one body, that when the system is taken out of equilibrium, then the natural tendency of the system to go again to equilibrium is described by this automorphism. Then we can describe here in this picture, like, for example, if we are, we have the body in this state, and this is put out of equilibrium, then with one process inside the same system, this go again to equilibrium. This is one element of the automorphisms that are described here in I note. In I note, I have one automorphism that are related or that are the morphisms of this set of morphisms here are elements, are the description of the set of automorphisms in this body.
Can I ask also the question of, say, that an automorphism might be an isomorphism in the sense that that the equilibrium state might be, say, an oscillation or something like something that is always changing. So not in equilibrium in one sense, but always changing in the same way, like an orbit, for example.
The idea that I put here for the automorphisms is that this is the description of the system. Okay, this is an internal process. I not used here the word equilibrium, but it's the tendency to put again in equilibrium to the system. Then the picture is not complete, but the element that is starting this process is one external element, for example, this. Then the interaction here put out of equilibrium at the body phi node. And then this start one internal process that is described by one automorphism that tends to take to the system again to equilibrium. This is that I am trying to illustrate here.
So I think about, for example, satellites orbiting the Earth, and these are in some sense in equilibrium. They don't fall to the ground and they don't get further away. But if we interact with the satellites somehow or another, we send a missile up or something, right? Then this will modify the equilibrium in some way, but it will eventually reach a new equilibrium, right, with having been disturbed in some way.
Yes, maybe following your idea, if we take the idea of the satellite, for example, this is the orbit of this, for example, and maybe something is getting out of this equilibrium state. But look at this. The description of the orbit is not exactly one equilibrium. Only time the satellite is correcting this here state because the interaction with the Earth. But here, anyway, we can say that this orbit is one equilibrium state, and something here is putting out of equilibrium. Then the system tend to go back to equilibrium and are going to oscillate around their orbit. This process is one internal process, but again, the process that is correcting the correcting the distance, for example, to this point, to this point, are one isomorphism.
Mm-hmm.
This is again one isomorphism. Then we have different ways of putting out of equilibrium to the system, but either this way is one interaction. Then any interaction is putting out of the equilibrium to the body, and then one automorphism is taking the system again to equilibrium. This is maybe in a colloquial way, we can say that this is the way that the body take aware of the existence or of the presence of the other bodies around him. This is the idea here with the automorphisms, because is the tendency to equilibrium is the way that the body take account of the presence of another body. In fact, it is not the external interactions, but the tendency to equilibrium is that make this change inside the body that is the way that he take aware of the presence of the external body. Okay, then I go to the next. And here, then we have now the definition of interaction. Then interaction is this composition that we have here. Is the action of the body 151 on the body 50, followed by the automorphisms that take to equilibrium again to the body phi naught. This is interaction. And here we can say this identity is the automorphisms that says to the body that he is in equilibrium, that it is in equilibrium. This is the idea. Then either that the phi naught is in equilibrium, then we can say here is acting E naught.
Can you remind me what is I01? This is, you called it just a morphism?
This is a Morpheus, yes.
But so if this is interaction and requires the recognition of an of I0 as well as I01, then I just wonder what is the name for, what is a physical name for I01?
Okay, the physical name, I put it action.
Action, yes, okay.
Action.
Yes, okay, good, yes.
Mm-hmm. Yeah.
Yes, so I01 is the action of phi 1 on phi 0.
Yes.
Not the interaction of I1 with I0.
No, it's the action of.
Okay.
Yes. Okay. Then this is here the definition. Then it is important to say that either we need this pair of morphisms in the interaction. Okay, yes, then I'm going to the next. Okay, this is only to put that there are one reaction of phi naught on phi 1 that is one interaction, one action I1 naught followed by one automorphism I1 that is taken again to equilibrium at the body phi 1. Okay, it's the same, but it's the reaction process. Then finally, we can speak here about composition, that it is important because, okay, here I illustrated the different kinds of interaction that we have in the system of bodies, phi 1 and phi naught. And then they are interacting reciprocally, and the system is putting one body out of equilibrium. Then there is one automorphism taking this in equilibrium again, and then there are one reaction to the other body that take the other body out of equilibrium, and then the other body start one process going to equilibrium again. Okay, and here is the associativity of morphisms. I think that it is one important point by your comment before, Professor Pech, because here with this definition of interaction, we have the associativity in this kind of morphisms that have the this associativity law. It is important to see that the associativity not only is this formal association in the binary operation that we are using, but the binary operation of composition, but is this associativity have one physical meaning, because here in the first picture, we can say that the body phi naught is one passive body that is affected by the body phi 1, and then the body phi not go to equilibrium, and because this change of equilibrium, this start one process that is the morphism 1 naught that acting on the body phi 1 that again starts one automorphism. Oh, excuse me, I have to connect this. Excuse me.
Okay, no, go ahead. Welcome, Dr. Santilli. I see that you've arrived to our meeting. I'm sorry if there was some confusion about the starting time.
With my eyesight, I may have missed it. I came at 12 o'clock sharp. Yeah, sorry.
I was also confused by the time.
Well, I perhaps didn't emphasize quite enough that there was the time of the seminar was fixed by a sort of international agreement, a UTC, and so that means that locally, when your time changes, there is an apparent time of change of the meeting, but not an actual time change.
So at what time it started?
It started at 11 o'clock at my local time, which is Eastern Standard Time.
Oh, which is also mine, yes, unfortunately.
Yeah. With this, in order to be exact about the time, it's necessary to do a conversion from 1600 UTC, or Greenwich Mean Time, to whatever local time you observe.
I'm sorry.
That's no problem. Of course, we have the recording, so for the parts that you missed.
Oh yes, definitely. Thank you. Definitely, I will listen to. I will look at the recording. Yes, indeed.
Okay.
Okay. Welcome, everybody. And we only was reviewing some ideas that I was presented before, but maybe we have the opportunity to discuss in more detail this. And then I was speaking here about the idea is was go directly to the presentation of the idea of the interaction in the using a categorical language. And then I started with the definition of the objects, the category of excuse me, the class of objects in this category, and then after we remain about the idea of morphisms in this category that are describing the action and the automorphisms that take to the equilibrium state each body. Then I was speaking here about the idea of associativity. Then it is important because how I say we can see here that the associativity law, but I think that this can have one interesting physical meaning. That is this. In the first picture, we have one description of the system in where each of the bodies are a passive body. Then the action comes outside the body, and the body goes to equilibrium again. And this change of equilibrium make one change in the systems that start the action of the body. For example, the body phi naught to the body phi 1. But this is one process of equilibrium of the complete system here. And then again, the body phi 1 tends to go to equilibrium, and this produces all the continuum change in the systems that are describing the interaction between these two bodies. But in the another excuse me, in the other picture here, the physical description is different because now phi 1 is one active body. Then one internal process in phi 1 start one automorphisms that change here its state, and then this change of state start the process I note 1 that is affecting or acting on the body phi naught. Then in this associativity idea, one have one different description because internal process in the bodies are starting the action of this body in another one. Then I think that it is important to say this because there are the different ways of read this kind of association of the morphisms. Okay, then I'm go to the next, and here is one important step, because when we have one body that are that are receiving that is receiving the action of more than one external body, then there is one process here that in the way that this can see the process like came in for only one body, only one body. Then we have here in this pictures the way that the total action of the external system are doing change of process here in the body phi knot. I think that we can discuss more about this because I have not. I'm going to put here one more picture with this idea. I have here two. Oh, excuse me. First, I need to put more. I have here phi1 and phi2, and here we have phi1 cross phi2, and here we have two projectors, P1 and P2. And here are the action in the body phi knot. Then these morphisms are I01 and I02, and this is I02 O1 plus 2. This is the relation between these two, these morphemes defined here.
So it's like a Cartesian product, or
yes, it's a Cartesian product. A Cartesian
from
product.
From the point of view of the objects.
From the point of view of what? Of what?
The object.
Of the object. Yes.
Like phi1 cross phi2.
Yes.
Is the pair of bodies acting independently?
Yes, the arrows body acting independently, but this unique
it's unique, right? Because it's universal, right? Because you said they are independent, so they cannot be more independent than being independent. But if phi1 and phi2 are also interacting, if phi1 had an action on phi2, then would you be discussing a more general notion of limit here, like in a categorical sense?
But here is one important idea, because in this decomposition, there are two projectors here. And the projectors is the way that the description that we made with the left side of this equation are wielded. This is one way of describing the systems that I think that it is important here, because it's like a kind of important axiom in the way of doing physics, because here we have not only this equality that we have, but we are postulating that this equality is valid. But this is because the presence, excuse me, I'm going to start this because I wanted to change color here. But this projector is equivalent to this composition of taking this to here, is this P1, and this to here, that is P2. Then we used to make the description in this way, but this is in one we need to pay one higher price, because we are forgetting the interactions here.
Mm-hmm. May I ask if you, Professor Cruz, whether you impose any restriction or limitation on the notion of interaction, such as the linearity, or could you please clarify for me
at the moment, I am not restricting this kind of interactions, because the relation needs not to be linear.
Thank you. Very important indeed. The admission of nonlinearity is very important.
Yes. I can say that at this moment it is not necessary to speak about the linearity of the interaction.
Thank you.
Okay. Then, okay, I understand this, and it is important to maybe we can add another more pictures about the relation between this kind of morphisms, because excuse me, I'm sorry, but here I need to go out and go back because I can change the color of the pen. I was speaking about to use this another representation of the system, because maybe internally in the bodies, then we have one change of this body that is going to another state because the action of the external body one. But if we have another body acting of this, for example, a body 2, then this take to another state to the system, to the body, that I call this phi naught 2. And then if both actions are affecting the body, then we have here the final state of the system, that's here IO 1 plus 2. And this is the internal process that is I not 1 plus 2. Then this scheme is referring to the internal process of the system. And then we have here one associativity diagram that we can use later. Then we can say that I O 1 plus 2 is equal to I O 2 I O 1, and then here is one important results, because we have here commutativity in the internal process of the system. Then this is the way that we are describing the process in the system, and I say that the comment of Professor Page before, in the way that how can this relation change if we include, for example, the interaction between the two bodies, Phi1 and Phi2. And I think that I need to explore that, because I have not included this idea here.
Yes, you intended to write that as a commutation there, the last equation? I think your superscript is exchanged. So that
Okay.
it's
Yes,
identical,
I write here. Yes, here and here. Thank you.
1, 2.
It's 1, 2. Yes, thank you.
Okay.
Okay. Then, but one important word here is the extensive. I am speaking here about extensive property. Okay, I put it here both words, but this is not applied in this scheme, because this scheme is only for extensive properties, and this is expressed here in this relation. Then the extensive properties of the system are described in this way. Okay. Then we go to the next, and here, okay, we have in the it's the same that I put that before, but now the idea of this lost interactions that the professor says before is illustrated here. Then we are, in fact, in this way, we are lost in this interaction, and then we take this in this way, in this form. And this is I01, and this is I02. But we are lost in, excuse me, I put it in the wrong way, this, it is here, okay.
Yes.
I01, and this is here are the projects that I said before. Then in this description, we are lost in information. about the system.
Yes, because we have also this action of 1 on 2 and 2 on 1.
Yes, yes,
This interaction is lost in the projection, right?
yes, yes.
So is there a
But
simple,
in the way
is there
that
an example of this, action?
excuse me,
Is there a simple example of forces or something of this interaction that you're describing?
for example, in the idea of mass, for example, in the idea of or for example, electric interactions in terms of charge, then we say that the electric field is the sum of these two electric fields, because we say that the total charge of the system is Q1 plus Q2. And then we are here adding these properties, and we say that these properties are extensive properties.
So it's like if you were far enough away from the charges, then there is no near interaction, right? So a near interaction would be different, right?
Yes, because we are lost in. Excuse me. Here I have one Q1, Q2, and we say that the description of this of the action here are from Q1 and Q2, but we are lost in this interaction.
So maybe I give another example, maybe that's also related. Of course, if you take the Earth and the Moon as a system, they both orbit the Sun, right? And the interaction between the Earth and the Moon is not very important from the point of view of the large scale, right? Like the
Yes.
if you look at the fine detail, of course, you're ignoring something about the fact that the Earth also the Earth and the Moon are orbiting, so that they don't, their orbits are perturbed a little. But if you consider only the Earth in its interaction with the Sun and only the Moon in its interaction with the Sun, then it's sufficient just to sum the mass.
Yes. And I am saying here that the one property I'm sorry, property is right, yes?
Maybe, perhaps.
Perhaps depends of the quantity of matter.
Yes. So the scalar field that it represents.
Yes.
The mass.
For the case of the Earth and Moon, is the at solar level is the center of the behavior of the center of mass for this of the system that essentially sets the trajectory. But then, as you, Dr. Page, as you correctly indicated, there are corrections, of course, because of the internal structure.
But you're ignoring tidal effects, etc.
But I think that the problem is here. We are assuming that this system is equivalent to this. For example, I can put here Q and Q not here. This is the problem. We are assuming that this is a valid way of description of the property of the system.
Of course, most importantly, in both cases of gravity and the electromagnetic field, inverse square law is involved, which is, of course, influences everything.
Yes, but excuse me, but I don't understand the comment.
Yeah, I was just remarking for gravity, the inverse square law, the distance, the gravitational strength depends on the square of the distance from the center. Whereas with the charges, it's the same way. There's something equivalent of Q1, Q2 plus Q2. The center charge is related then to the center of gravity.
Okay. Okay, because the model that we use to describe the gravity interactions take to us to use the total mass or electric charge in this case in this way. But I think that the case here is that we are describing the properties of the systems with one linear description. This is, I think, the principal point. And we used to say that in physics there are two kinds of properties, extensive and intensive properties. And even we say extensive properties, we sorry about the addition of the properties. And this supposes that the total property is only the sum of these properties.
It's almost like the Lie group in Lie algebra. In Lie algebra, you're interested in the sum, characterizing the sum of two elements, whereas in the Lie group, it's multiplication.
Okay. Yes. But then I think that this is related with the idea that we need to express the interaction taking account of this internal interaction in the systems. And then the resulting property are not more the addition of these separated properties. I think that this is the principal idea here. Okay, I don't know how much time I have.
Yes, as I was going to mention, you started at 15 minutes after the hour, so I think it's reasonable at least that you have until 15 minutes before the hour, which means another 10 minutes, I guess.
Okay. Okay, thank you. And here is the other properties. The interaction intensity are related with the intensive properties. And I wanted to take here the example that Professor Garrett used before. For example, in the gravitational interaction. If we have the same mass, but the distance is different, then the intensity of the interaction is different. Then this is expressed in this morphism. In these morphisms, the intensity is expressed, and this is the this is related with the intensive properties. Then it is important because here we have not only the description of this kind of properties. I am going to put here, for example, for intensive properties, we have this. Okay, I use IO not 1 plus I not 2 equal to I not plus 1, 2. This is the relation for extensive properties, but for intensive properties, we only need to see about this, for example, or about this. And here in the, okay, not necessary, excuse me. And here, this is intensive, and this is extensive. Then, and we can see this in this way. Here we need only the information that about the action of phi j on phi I. Only that we need only that information. Then this is like the idea of one measures that is made using only one using only one action, or only one action. I'm trying to explain in a different way. I remember to use the idea of the electric circuit. Then the idea that we use to measure the current here with the is doing cutting the wave of the current here, and this is the process that we use it to determine the intensity of the action. We cut that action and then go to the equilibrium state. And when we use to measure the voltage, we not need to cut the system, but only need to use 2 points here. Then the intensive properties are measured using only 1 point, and the measure of extensive properties are getting using lectures in 2 points. Then we have here covectors, and we have here vectors. This is the principal idea. And then the product, for example, of the vector and covector take to us to the scalar that is here, for example, the potence of the in the circuit. Then this is the way that we take in general the measurements of the systems, and is the way that we get the information for extensive and intensive properties. Then I think that in conclusion, because I have not enough time to abord another subjects, but in conclusion, I only in this opportunity get to present the principal concepts of the category of equilibrium bodies states. And then in this way, I introduce the idea of interaction and the idea of description of the properties of the system that are the extensive and intensive properties. Okay, then I think that I am going to stop here. Thank you very much.
Okay, I think we do have time for questions.
Yes.
And maybe, I mean, of course, anyone can leave if they have other commitments and review the video later. But I'd like to take at least a few more minutes for questions. My first comment is I feel like we only get to the point where it starts to become really interesting, and unfortunately the time runs out. But this idea of measurement is like how you describe measurement becomes very exciting to me, especially when you say that we have here a physical model for vector and covector. It's like, oh, that's a very different point of view about the relationship of measurement to vectors and covectors. I guess maybe what I wanted to say is that that if we think of vectors as operators, then covectors are another type of operator that maps vectors into scalars, and so it's a little bit hard to see that notion of covector when you relate it to, say, a 2-point voltage measurement. I don't
That's
see-
right. I'd like to see the details of that description too. How do you use a covector to measure voltage across a resistor, or a vector, well, for a voltage, for current? Well,
Yeah.
Yeah, for current, it's easy to see that it is somehow related to a vector. It's a current, so it's like a flow. But for potential, it's strange to see it as a covector.
May I
I'd like to
suggest?
see that too. Maybe Jesus can clarify that.
Yes, in fact, I can put it here. Potential, different differential of potential. And then, in fact,
I see. So what you're measuring is a difference, of course.
excuse me?
What the voltage measurement is a difference in potential,
Yes.
whereas
the
the
difference
current
in
is
potential.
the current is not a difference of anything,
No.
right?
No. It's not a difference anyway.
So it's like delta V.
Dr. Page, may I suggest that perhaps you can elaborate a little bit? You have your next lecture next week. Perhaps you can include, a few comments on, this is an intriguing point, of vector and covectors, in geometry, the geometry of the measurements.
Yes, certainly it's related, and I hope that I can say something useful in that regard. But as I mentioned earlier, I guess I hope that our meeting next week can be more interactive and more discussion oriented. Although there are a few things in particular that I would like to say.
It will start at 11 o'clock our time.
Yes,
Okay.
correct.
Thank you.
I'd like to also mention this new article in Scientific American about what they call infinite category theory. It's an extension of the usual category theory to infinite dimensional spaces. In fact, I was wondering is there electronic version of Professor Ojevich's new book on category theory available? It might be helpful if we could see that.
I'm not sure. Was it published in English?
Yeah, I don't think it's in English. Bishop Ojevich's book is not in English, is it, Jesus?
The book of Professor Osiewicz in category theory.
Yeah, exactly. There's no English.
Yes, it is published in English. Yes.
Oh, it is in English too, then.
Or maybe in Spanish. Yeah, I don't know.
You don't have. Do you have an electronic version of that book? You have
I don't remember this. I have the one electronic version, but if I have, I can send it to you. Yes.
That'd be very helpful.
Yes.
This is the October version of Scientific American, has a very interesting article about category theory. That's very readable. It summarizes the ideas of what you're talking about.
Okay. Okay. I'm going to see that. Okay. Thank you, Professor.
The Spanish version is well, the translation of the title of the Spanish version is Graphs of Graphs. And then the subtitle is Introduction to Category Theory. So it's generalization of category theory to perhaps in other ways, I think. And
Yes.
it's like,
Only in a Spanish version, I think so.
Maybe I have some version, old version of this, but I don't know. I need to look for this. Mhm.
Thank you.
Okay.
all right. Well, I appreciate everyone's attention for our meeting today, and we will continue next week on a slightly different but related subject. And I'd like to advertise again that we need suggestions or recommendations or offers for presentations for future meetings. So if you have any ideas or would like to suggest a particular subject that you would like to talk about, please send me an email. We can bring it up at our next meeting.
I made a list of Dr. Page. I made a list of potential topics in my last email to you.
Yes, I appreciate that very much, Dr. Santilli. And so your list is very extensive, of course. There are many aspects and subjects related to the ISO theory, and I think it would be quite appropriate for us to decide, perhaps collectively, on the most sort of highest sort of priority in terms of which particular subject relating to the ISO theories is of greatest interest at this point, because it's such a wide field.
I might
In my
have
own case,
a suggestion about that. ISO Lie algebras versus geometric algebra Lie algebras. I'm sure they're very closely related. I've been in communication with Dr. Santilli about this. I think we could do something more with that very soon, actually.
Yeah, that's also interesting. Yes, indeed.
I have a sort of related question, I guess, is that when I've started to look more deeply at isotopy in general, I'm starting to wonder about the relationship between isotopy of the field, so ISO numbers, compared to the isotopy of the algebra, the Lie algebra. And it seems to me like clear that they could be related in some way, but it's not so obvious to me how. And in particular, when we look at the way that Oshevich defined vectors as derivations on a field, then if we start with an iso field and consider derivations of the iso field, we still define the Lie algebra in a very similar, like a way with our definition of Lie algebra is going to be just the operation of one derivation on another derivation minus their commutator, and so I don't see the isotopy arising there naturally because of the isotopy of the field. But maybe I'm missing something, and that's
Is the isotopy is in the derivation. There has to be an iso derivative. At least I know this would be my first.
Yeah, as you explained in your lecture or your previous lecture, Dr. Santilli, you discussed isocalculus and how the derivation changes, but I don't like. It seems to me like an extra assumption to say that there is isotopy at the level of the Lie algebra. Is an assumption in addition to isotopy at the level of the field, but maybe I just...
Well, the algebra are based on universal enveloping associative algebra. The moment you the moment you assume an isosociative algebra, automatically you get the Lie isotopic algebra automatically. The problem is that so this comes very natural. However, for consistency, because otherwise there are very hidden problems here and there. For consistency, then the Lie isotopic algebra are able to be treated with the full isomathematics. That we see it. If you look at my first book on Springer-Verlag, that was derived in a very empiric way, but was defined on an ordinary field, and the elaboration was based on ordinary differential calculus. But we had, when we passed out the application, we had a major problem. So first we had to reformulate everything on an iso field, but then was not enough. We had to reformulate, we had to elaborate the Lie isotopic algebra with the isodifferential calculus. Otherwise, it is a single body as far as we can see, that monolithic. If we change one, there may be, but particularly from a physical viewpoint. See, remember my comment on and Professor Georgiev work on isodifferential calculus. He defines on an ordinary field. He's a mathematician, absolutely no need to define on. So what my words indicating there are problems that are problem in the physical application, not in mathematics. No, for instance, your viewpoint of introducing Lie algebra as an additional axiom. Yes, you can be done as a, and in mathematics, yes.
Maybe
Just going to relate it back, to what Dr. Sochik said, is the relationship between Clifford algebras and ISO theory.
Okay, maybe we could just talk about ISO number. What do we mean by an ISO number? I like to compare that with a geometric number, vector, bivector, 3-vector, 4-vector. There must be some relationship at that level of basic ISO number. What is an ISO number?
Yes, well, ISO number is a volume, projected in our.
What kind of volume? A 1 volume of a 2 volume, 3 volume, n volume?
Just an ordinary thing. Think, the most elementary way, think about, a spheroid. Think about the shape of a proton and a neutron. That's basically, at least that's the intent.
But does that mean a 3-dimensional volume, like a,
yes,
could it be 4-dimensional volume or 5-dimensional, 6-dimensional?
ISO unit has 3-dimension in for non-relativistic application, or 4-dimension if it is in a relativistic application. Could have
so can you say an ISO number is a determinant then that represents volumes?
If you want, you can express it in that way, but in the way to be as line as possible on with the Einstein-Podolsky-Rosen paradox. The problem is to remove to replace the locality, in his words, the locality of quantum mechanics, which is everything defined on a point, everything a point. To pass it to the physical reality that in the nucleus, the proton and neutron have to be extended. So this to represent them with their shape. And that shape is we try to represent that shape with the ISO unit. And the reason why we have some hope of doing it is because in the notion of ISO number, the ISO unit, in the isotopy of an ordinary field, there is no need that ISO unit has to be an element of the original field. So it can be anything you can wish of. And now you can use a vector or there is no restriction on what it can be. And the ISO number is the product of the original number multiplied by the ISO unit.
Clearly, we do have a lot of things that we can discuss on this subject, and so I guess what I would like perhaps is to decide on a topic that would cover these ideas, and I, for me at least, these ideas remain, the issues of mathematics, of understanding the mathematics. When the physics gets involved, it seems to me to obscure the mathematics in some cases. So I don't mean, of course, that we want to do it in a just purely mathematical way, but I do like to be able to understand the formal structure of the mathematics first, right? With only just the understanding that the motivation is physically motivated. But so at the moment I've been reading mostly the mathematically oriented literature, and I seem to get only so far and then get stuck each time, mostly because the documents that I've seen so far transition into physics rather quickly. And I think, well, gee, we're talking about physics, and I haven't understood the mathematics yet, right?
But if I may have a comment, that's a plus, because I indicated a number of times, despite the work done so far, especially from a mathematical viewpoint, there is so much to be done. Oh yes, indeed. And also most of the idea were developed by physicists, that I'm not a professional mathematician. I am everything.
I do like the idea of associating it with geometry somehow.
Yes, of
geometric
course.
algebra or Clifford algebra,
Yes.
without going into the physics of it, but going into the more
pure mathematics, yes.
Intuitive mathematics that you associate with geometry, as opposed to the more abstract mathematics.
So that's why I mentioned this ISO number. I'd like to pin that down as much as possible.
But it's like the Hilbert spaces, infinite dimensional Hilbert spaces. I know how to, in my very, very limited capability, I know how to use it and extract numbers. If you ask me what is an infinite dimensional Hilbert space, I have to be honest. And I said, I don't know. With ISO number, there is something, hydraulic. If this is a problem for quantum mechanics, it's multiplied when you pass to hydraulic mechanics, because nowadays finally we know how to operate, but the understanding number of many notions, and I agree fully with Dr. Page, the correct and comprehensive formulation, mathematical formulation has been done only partially. The best formulation mathematical is that Professor Ganformina and Nunes, because they use both ISO number and although they're very limited in the partial differential equation. The beautiful book by Professor Zagas on Lie isotopic algebra, but unfortunately at that time ISO number had not been discussed, so we could not apply his results. And mathematics, beautiful mathematics by Professor George, we formulated on an ordinary field, and that's not it's inapplicable. We cannot use it in physics. So
let's just agree tentatively that we'll have some type of presentation on a subject closely related to these questions on December 1st. I believe would be the next meeting after, well, in 2 weeks' time. Is that okay, Dr. Centilli?
For me as a speaker, unfortunately not, because I have to prepare the paper for the proceedings of the meeting dedicated.
Oh, yeah.
Yes, so unfortunately.
Okay, well, if you could propose a date, a Wednesday, and a time that's convenient, a date that's convenient for you.
Yes,
usual time.
I'll be happy to do so. I have, in case you have a vacancy, namely you have no speaker, I have a number of lectures that can be included. We have a long list. Yeah, we have a long list. If you look at www.lecture-series.org, Word lecture, we have 15 levels of many different lectures. Some of them, most of them are physics or physical, but some of them are indeed in mathematical. We have also we have the recording of the lecture by Professor Georgiev on the recent Congress on isodifferential calculus, but it's on highly specialized. So if you have an interesting, as far as I'm concerned, and I don't want to abuse of your time, but I was listening this morning while having breakfast to the BBC and was making a report on the global warming, and was shocking. In Canada, they were reporting apparently 500 deaths this summer on the west coast of Canada because of extreme heat. On the east side, 100 deaths because of incredible rain, and the tragedy in Mozambique, that is 4 years of no rain. So my personal my personal preference, if you ask me, I did not know. I gave you a list because I didn't want to impose, because I don't know the priority. Priority have to be decided, collegially. But if you ask me personally, my personal mean will be to work the mathematics and then the actual application for new clean energy. It's called intermediate control and nuclear fusion. They require, I cannot do it with isotopy because isotopy is for a reversible system. Fusions are irreversible, so I have to necessarily. So if you ask I will say, let's look at the admissible completion of the Lie isotopic theory, and then above all look at the application, because sometimes in the application they will give you a hint of what is missing from a mathematical viewpoint. That would be my personal. But again, I don't want to impose it. I have no intention whatsoever of imposing it.
Well, I feel that I personally also am very interested in this idea of intermediate fusion. Of course, it's very controversial and not popular in physics to consider alternate fusion. But this topic, this seminar, cold fusion or low energy nuclear reactions, or there's any number of words that have been sort of used to soften the controversy to something that's more acceptable. So I do personally have a strong interest in this, but it does seem to be somewhat outside the idea of fundamentals of physics. So it's just, I hesitate to say, let's go for a more application physics oriented lecture. For me, that would be okay, but it is perhaps, maybe Jesus and I have to talk about it more.
Yeah, I'm willing to give a talk too, but I'm really pressed. I want to finish my paper for the memorial proceedings, which I'm working on right now. Yeah. But that's due at the end of this month, so next month, then would be all right sometime.
Yeah. Okay. Well, let's just meet next week, and maybe if we have different ideas at that time, we can state them.
Maybe just have a general discussion next week. No topic, but just more talking like we're doing now might be interesting.
Sure.
Great idea, Dr. Garrett. Yes, it will be fantastic. We can have an agenda of topics in which we can discuss freely. Because, for instance, I would love to know in more detail the concept, the conceptual difficulty that Dr. Page is having in grasping isomathematics. So in the discussion,
I can certainly if I give some discussion. At least in the introductory comments, I can be a little more elaborate about how I would see, isotopy in relationship to vectors as derivations.
For example, also differential forms are talk about volumes all the time. Covectors and so on. That's language of differential forms as well. So that's a course of derivation as well. So all these things are related, of course.
Yeah. Okay. Well, thank you very much. I think we do need to say that it's time to quit. So I'll announce the recording as soon as it's available. In now, which I think I'm continuing to use the YouTube place to store them, so you should. I'll send you a link to that. And so for now, is say goodbye and thank you very much, Jesus, for your
Okay.
presentation. And
Thank you.
you also,
Thank you to you.
I think you also have a lot more to say on this subject. So, but maybe we can continue, when you feel that it's time for you to do it again.
Yes.
You're very interesting.
I'm going to
category.
look for this. Yeah. Thank you.
Okay. I enjoyed your talk. Awesome.
Thank you, Professor Alice. Yeah. Thank you all to you.
Thank
Bye
you,
for
Dr.
now.
Goodbye, everybody.
Professor Cruz. Sorry, I missed the original part of your talk, but I'll listen to your of the recording. Thank you.
Thank you. Thank you.